Hello and welcome to this pre-lab video for lab V13. This is a virtual lab for our week 12. It is on KSP, the solubility product constant, and the solubility of salts. So in this pre-lab video, I will go through some of the theory and the concept behind KSP, which we should have some familiarity with already. We'll get into some of the calculations. I'll talk a little bit about the pre-lab, and then I'll roll straight into the actual exhibition of the lab and do just a short walkthrough of what it is that you're expected to do. So without any further ado, let's kind of get into this. Now, solubility equilibria is based on the whole idea that everything that we've talked about thus far about solubility is kind of a half-truth. When we gave you solubility rules, what we told you is that certain substances, certain ions were usually soluble, certain ions were usually insoluble. But solubility isn't really an absolute. Things aren't always soluble or always insoluble. Even things that are really, really soluble do have a limit to their solubility. We cannot just infinitely dump sodium chloride into water and expect that it all will dissolve. At some point, we run out of space for those ions. And when we do, we enter into an equilibrium. That equilibrium has the undissolved solid on the one side, the reactant side, and the dissolved solid on the other side, where it breaks apart into its ions. And there's an equilibrium that exists between them when we hit that solubility point, where we can't get it to go any further. We call that saturation. Well, all that solubility is just a varying mark of where saturation actually occurs. And so for the things that are very, very, very soluble, that means that they have a saturation limit that is very, very, very high. And for things that we consider to be insoluble, they have a saturation limit that is very, very, very low. But the thing is, even the things that have saturation limits that are low still dissolve to some amount. It may not be in a very appreciable amount, but it does dissolve at least in some way. And we can quantify that solubility using KSP, the solubility product constant. So I give you an example here on this slide about magnesium hydroxide. Magnesium hydroxide is a weak base, first of all, but as a solid, it is really not very soluble in water at all. That's not because it's a weak base, but that's just kind of how it is. Even the ones that we consider to be strong bases, like calcium hydroxide, have relatively limited solubilities in water as well. But their weak base attribute here means that it is in equilibrium, and in equilibrium, we can quantify its ion concentration based upon this value known as KSP. And so all of the concepts that we've talked about to this point about heterogeneous equilibrium, they still apply here. So because this is a solid here, it is not going to be in K, which means that K is going to be equal to the concentration of the magnesium ion multiplied by the concentration of the hydroxide ion squared, because those still apply as normal. And so all that we've done is we've changed the subscript here, KSP, since we're now talking about a solid product, a solubility. So KSP, SP standing for the solubility product, K being the constant. Now, when we express solubility itself, there are two ways that we can express solubility. The first one, the one that we are probably the most familiar with, is mass solubility. How many grams of a solute will fit in 100 milliliters of solution? This is the one we've quoted the most often. Sodium chloride has a solubility of 70.1 grams per 100 at room temperature. But for our purposes, we're actually going to focus more on this molar solubility business, moles of solute per liter of solution, because if I can get that, that's molarity. And we already know that molarity and K values are compatible. And so I can find the molar values, plug them in directly into my KSP expression, find my KSP. Or, working the other way, I can take my KSP values and backtrack them and figure out how much, what the solubility is in terms of molar solubility. And so let's do a couple of examples with these kinds of calculations to kind of get on the right foot here. So what is the expression for the solubility product constant for calcium fluoride? Well, the balanced chemical equation would look like this. Calcium fluoride becomes calcium ion, aqueous, and 2 fluoride ions, aqueous, which means that KSP would be the concentration of the calcium ion multiplied by the concentration of the fluoride ion squared. Again, we don't include the calcium fluoride itself. It's a solid, and solids do not change appreciably in concentration, so we exclude them. Now, if KSP were equal to 3.9 times 10 to the negative 11th, what are the equilibrium concentrations for calcium and fluoride? So this is where we're going to take that familiar concept of an ice table or a rice table, depending upon what your instructor likes to call it. And we're going to apply it to a new situation now. So I've got calcium fluoride in equilibrium with the calcium ion and 2 fluoride ions. And my initial concentration, again, I don't care about the calcium fluoride, but before I throw any of that solid into solution, I know I'm going to have no calcium and no fluoride. And so the rest of my ice table is going to kind of look like that. I don't care about that. I'm going to gain 1 part calcium ion, and I'm going to gain 2 parts fluoride ion. Again, because of the stoichiometry. So at equilibrium, I'm going to have 1 part calcium, I'm going to have 2 parts fluorine, and now using my KSP and my expression here, I'm going to substitute in 3.9 times 10 to the negative 11th is equal to the concentration of calcium, X, multiplied by the concentration of fluoride, 2X, squared. X times 2x squared would give me 4x cubed, because 2x squared is equal to 4x squared. And so if I do a little bit of manipulation, pulling out my calculator here, 3.9 times 10 to the negative 11th divided by 4 would give me 9.75 times 10 to the negative 12th is equal to x cubed. Don't worry about the significant figures here. We'll fix it by the time we get to the concentrations. Now I need to take the cube root. Cube root gives me 2.1 times 10 to the negative 4th molar for x. And so the concentration of the calcium ion is that 1x, 2.1 times 10 to the negative 4th molar. And the concentration of the fluoride is equal to double that, which would be 4.2 times 10 to the negative 4th molar. So there are the values that I'm ultimately interested in: calcium ion and the fluoride ion. So that's how you use this information. So this particular case, we were able to find the equilibrium concentrations. Now, mind you, if we were asked for the molar solubility, is always equal to the X term. So if we were asked for the molar solubility of calcium fluoride, we would say that the molar solubility is this, 2.1 times 10 to the negative fourth molar. And so even if our stoichiometry comes out as 2 to 3 or 4 to 5 or whatever the case may be, whatever our value of X is, that is our molar solubility, because that's going to be the coefficient on that one ion, or that one atom there. So let's move on to another example. If the molar solubility of calcium fluoride at 35 Celsius is 1.24 times 10 to the negative third molar, determine the value of KSP. Well, since we just went through that, we know that calcium fluoride breaks down into calcium ion and 2 fluoride ions. Again, the molar solubility is equal to X. So if we went through the production here, it'd be exactly the same as the ice table that we just did, which means that it would be 1.24 times 10 to the negative third molar for calcium, 2.48 times 10 to the negative third molar for fluorine. Again, we're just doubling X, which means that KSP is equal to the calcium concentration, 1.24 times 10 to the negative third multiplied by 2.48 times 10 to the negative third squared. Taking those values, to 3 significant figures this time, I get 7.63 times 10 to the negative ninth. That's the value of KSP here. So remember, at 25 Celsius, the previous problem, it was something on the order of 10 to the negative 11th. Here it is at 10 to the negative 9th. So it is more soluble at hot water. And that is usually the case that we see. Hot water does increase solubility because it's putting more space in between the water molecules, and we've got better interactions. And in general, we tend to see that solubility increases with temperature. In our second one, we've got 0.0490 grams of silver iodate dissolving per liter of solution. What is the KSP? Well, let's start with a equilibrium expression. And this one is pretty straightforward. Silver iodate will dissolve in a 1-to-1 ratio of silver ion and iodate ion. So making up our ice table, we're going to gain 1 measure of silver, 1 measure of iodate, which means that at equilibrium, they'll each be X. Now we just need to figure out what the molar solubility is. To figure out the molar solubility, I need to turn this grams into moles and take you back to your Chem 105 days. We just need to convert the grams into moles using a molar mass. So I need the molar mass of silver and the molar mass of the iodine and the oxygen. For silver, it is 107.87. For iodine, it is 126.90. For oxygen, it is 16, and there are 3 of them. Total mass, 282.4 0.77 grams in 1 mole. So my grams will cancel. I'll be left with moles per liter, which is molarity. 0.0490 divided by 282.77 to 3 significant figures is 1.73 times 10 to the negative 4th molar. And that is our X value. So KSP would be equal to 1.73 times 10 to the negative 4th multiplied by 1.73 times 10 to the negative 4th, which would give us a value of 3.00 times 10 to the negative 8th as the KSP value for the silver iodate. So not too terribly difficult, these kinds of problems. You just got to know how you got to set up your ice table. Again, the ice table looks a little bit different because there's nothing on the reactant side, but setting that up and kind of doing the rest helps out a lot. What is the solubility in grams per 100 and the molar solubility for magnesium hydroxide at 25 Celsius? KSP value 5.6 times 10 to the negative 12th. So this is the same problem that we were looking at in the beginning, the solubility or lack thereof of magnesium hydroxide will give us magnesium ion and 2 hydroxide ions. Setting up this modified ice table, again, don't need anything on the reactant side because it's solid. Initially speaking, we have a 0 and a 0 here. We're going to add 1 measure of magnesium and 2 measures of hydroxide, which are going to give us 1 measure of magnesium and 2 of hydroxide at equilibrium. So setting it up, 5.6 times 10 to the negative 12th is equal to X multiplied by 2X quantity squared. Again, probably the hardest part of this is remembering that those coefficients travel here. And so overall, this is going to give us 4x cubed like it did in the first problem. If I solve it out, 5.6 times 10 to the negative 12th divided by 4 gives me 1.4 times 10 to the negative 12th is equal to x cubed. X is the cube root of that, which is 1.1 times 10 to the negative 4th. Molar. And remember that this value is the molar solubility. So we've already addressed the second part of this problem. We've got the molar solubility. It's 1.1 times 10 to the negative 4th molar. To turn it into grams per 100, I need to do a couple of modifications. First of all, I am starting with 100 milliliters of solution, not a full liter. So I need to start with the 100 milliliters of solution. Multiply this by our molar solubility. But first, we need to turn that milliliters into liters. One liter of solution is 1.1 times 10 to the negative 4th moles of magnesium hydroxide. Last step is to go from moles of magnesium hydroxide into grams. So I need the periodic table again. Magnesium is 24.31. Oxygen is 16, and there are 2 of them. Hydrogen is 1.01, and there are 2 of them. 58.33 is the total there. So 100 times 1.1 times 10 to the negative fourth times 58.33 divided by 1,000. We get 6.4 times 10 to the negative fourth grams per 100 milliliters. So not a whole lot dissolved, and again, that makes sense. Our KSP value is relatively low. Okay, so now let's move on to Lab Archives itself. I think we'll get a lot out of looking at this now because we'll have a pretty good understanding of what it is that we need to do. So from the pre-lab standpoint, in the pre-lab here, we're doing okay. For number 1, calculate the concentration of sodium ion in 0.269 molar sodium chloride. Well, what we have to remember is that the mole-to-mole ratios all translate. So the concentration of sodium chloride is the same as the concentration of the sodium ion and the chloride ion, since they all exist in this 1-to-1-to-1 fashion. Question number 2 is relatively straightforward. We're just going to do the same kind of thing that we did with the others. Make that modified ice table to figure out what the final concentrations are. Number 4, very similar to the problem that I just did in the PowerPoint. Use the KSP to figure out the concentration of, to figure out the molar solubility of copper-2 chloride, or copper-1 chloride rather. Then do that stoichiometry dimensional analysis thing to convert that to grams per 100. Number 5, you're going to reverse that. You're going to turn this into a molarity, which is going to be your X value, and you can take that from there to find KSP. The one that's kind of tricky in here is number 3, because in number 3, now we have, up until this point, we have been focusing on scenarios where we start with 0 reactant. And it's worked pretty well for us. But now it doesn't work that well for us because here we are told that the barium concentration is not 0. It's in fact 3.5 times 10 to the negative fourth molar. And so when we do our ice table, there's an extra factor that we have to put into this. Now, depending upon the overall situation, when we go to do the calculation, there's usually something that we can kind of work around. Now, the thing that we have going for us here is that the concentration of barium that we are using is pretty big, 10 to the negative 3.5 times 10 to the negative first. In other words, 0.35 molar. And relative to what we're going to get out of this on its own, this concentration is high enough that it's going to make enough of an impact that we can largely just ignore this positive x term. And if I do that, if I ignore that positive x term, this becomes 3.5 times 10 to the negative first multiplied by 2x squared. Now again, why can I do that? Well, it's a matter of the value of x relative to the value that we're starting with. And if the value of x is not going to appreciably add significantly to that concentration, we can ignore it. It's kind of it's our version of the 5% rule for KSP. Now, when we do this, that means that we can kind of simplify everything and make it work. Now, if this weren't the case, if this value was something like 10 to the negative fourth, just for the sake of argument, then what we would run into is we would run into having this kind of blow up on us, where we'd end up with a more complicated kind of reaction. 3.5 times 10 to the negative fourth plus x multiplied by 4x squared. And now I've got to expand this, and 3.5 times 10 to the negative fourth times 4 is 1.4 times 10 to the negative third, x squared plus 4x cubed. And so I end up having to do kind of a complicated reaction where I'm going to have to make a cubic equation. The cubic equation, 4x cubed plus 1.4 times 10 to the negative third x squared minus 1.84 times 10 to the negative seventh is equal to 0. And I'm going to have to find some kind of a cubic solver to do that. And yes, there are places where you can do that on the internet, and some calculators have that capability built into them. But certainly if we can avoid doing that, we're going to want to avoid doing that. So that's the pre-lab assignment. Let's move on in looking at the procedure itself. And you see that in the procedure itself, we are going to be using the Chem Collective's workbench again. So control click to open up the Chem Collective. We're going to the virtual lab right here, and we are going to upload an assignment. It is here in solubility in solids. It is the determining the solubility product constant. And so what you have here are a series of solids and some water. And really what you're going to do, if you follow along in the procedure, is you are going to do a couple of things. First of all, you're going to do an assignment. You're going to go through this and make a procedure. So we are kind of making this a little bit more open-ended in terms of what do you need to do to determine the solubility of the salts. Now, one of the easier things that you can do is if you take this distilled water and you take whatever it is that you're interested in. So I'll take calcium phosphate here. Right now I'm being told what the calcium phosphate has in it. Right now I'm also seeing what's in the water. If I add some calcium phosphate to this, let's just say that I want to add 5 grams. I put in my 5 grams, I look at the distilled water, it's going to tell me, okay, of my 5 grams of water, or excuse me, of my 5 grams of calcium phosphate, the concentration of the calcium is 3.4 times 10 to the negative 7th. The concentration of the phosphate is 2.27 times 10 to the negative 7th. Something important to note, once we hit that solubility limit, It doesn't matter how much more we add. Notice that the values here did not change. We've hit the solubility limit. So really what we're trying to look for is, what is the solubility limit? And when you go to the data and calculations section, you're going to make your own data tables here that are going to show the concentration of each ion, your calculation for the KSP. And then you're going to do some work here with the common ion effect, where you look at, first of all, how much each of these materials do you need to get the concentrations at this level? And then how much silver chloride actually dissolves when you do that. So that is ultimately what you are going for in this experiment. So the procedures here are very, very open-ended. There's a lot of different ways to go about doing the problem. But you are going to need to show in your data tables how you did the experiment, what you did, what kind of steps you took, and what the data ultimately were. For the post-lab questions, the post-lab questions kind of follow along with the pre-lab in terms of finding molar solubilities, showing your calculations for those, finding your molar solubilities finding your gram per liter solubilities in terms of your common ion solutions, and just a general analysis question about KSP. So if you have any questions about this lab, feel free to reach out to me either during our in-person sessions that week or any other time via email or remind. I'll be happy to help you out there. But that's all for this particular pre-lab video. I'll see you in lab.